So it's my pleasure to announce the second speaker this afternoon, John W. Pratt from the Business School at Harvard. Dr. Pratt may be known to you from many aspects as an author of some books or as an editor. I want to share with you one secret which he told me this morning. That's the W, which is between the John and the Pratt. The W stands for Windsor, and it's actually the same Windsor that we know in statistics from Windsorization. Windsor was his uncle, so in the Pratt family, Windsorization is called uncleization. The talk this afternoon is dividing the indivisible using simple symmetry to partition variance explained. Dr. Pratt.
Thank you. First, I guess I should say that I think I'm the only member of the family that knows what Windsorization is at the moment. So some of what you heard is not altogether true. I also might save a little time by saying that I agree with everything that Terry said, although I won't repeat it, about the pleasure of being here and how nice it is to be invited. The kind of problem that I want to talk about actually I think probably has a good deal of relation with what he was talking about, and he probably knows much more of the history of it than I do, so I won't try to go into that. It does have a long history. What I know, I guess I've learned mostly by cribbing from papers by Bill Kruskal and looking up some of the things that he mentions. For example, Yule in 1899 was interested in why the percentage of people who are paupers varied from place to place in England. And Williams and Mosteller in 1947 were interested in the relative roles of education and economic status as determinants of opinions. And Kruskal's been looking at some of the legal literature on the contributing factors in accidents, and the legal people would like to assign responsibility in some way. I don't think they begin to appreciate how impossible that is, but that's another matter. And of course, a very popular question is how much is due to environment and how much is due to heredity in all kinds of situations. Now, so I'm talking about partitioning variability among sources, and in particular in a multiple regression framework. Now, I recognize that it's dangerous to answer such questions at all, because even if you have a stable mechanism and you have all the relevant variables, the distribution of the x variables, the independent variables so-called in the regression, makes a difference to the kind of answers you get. If you're in a place where education is uniform, it can't really play much role in explaining differences. And similarly, if economic status is uniform, as some countries aim to have it, supposedly, then it can't explain much variability. Nevertheless, assigning relative importance to variables is a very natural game to want to play. And it is often played, and outstanding statisticians such as Yule and Mosteller have played it. So I'm going to talk about it. Now, if you could specify enough particulars in your problem, the decisions it's possible to make, the costs of making the decisions, the benefit functions for the effects on the dependent variable, and so on, you could give a satisfying answer, but the measure that you would derive would be very specific to the particular application that you were involved with. And in most situations where people want to talk about how important the various variables are, the context seems to be much less specific than that. That is, suppose that the joint distribution of your y, we have some explanatory variables and a dependent variable y. Suppose the joint distribution of all of them is known. How can we assign relative importance to the x's on the basis of that joint distribution alone, with no decision structure, no cost parameters, or anything like that? Now, I'm ignoring sampling error as I guess Terry did, because that's not the issue here. The issue is even if you knew this joint distribution, how would you partition the variance? Now, what I do in the paper is to look at some requirements that it's natural to place on any measure of relative importance, or at least I claim it's natural, in such a situation. So you might call them axioms. And it turns out that these restrictions, natural restrictions, essentially determine the measure that should be used, at least I would say so. It is a measure that has sometimes been used, but apparently it has been viewed so far as arbitrary or even ludicrous, or at least that's what Kruskal's reading of the history seems to suggest. If people know otherwise, I would like to hear about it before I say anything too embarrassing in print. So now let me get a little more specific and try to give you a sense of the argument. I want to cover up some of this you're not supposed to see yet. So I'm going to start. How are we doing? From a model in which y is explained by a bunch of x's, and let's suppose to start with that the whole thing is completely symmetric. So the x's all have the same variance, they all have the same correlations with one another, and the regression coefficients are all 1, or if you like, the correlations with y are all the same. Never mind what the residual standard error is, that doesn't matter, but that would be all part of the symmetry. Okay. So the situation is completely symmetric. It seems inescapable that you're going to say, in this situation, that each xi explains a fraction 1 over the number of variables of what's explained. Okay? So if you agree to that, then let me rewrite the problem somewhat and point out that if I introduce a variable capital X1, which is the sum of the first m x's, and capital X2, which is the sum of the rest, then, of course, the regression of y, I'm dealing with everything in the regression framework, so just the first two moments. No normality assumption. Where is he? The regression on X1 and X2, since the regression on all of them would be X1 plus X2, the regression on X1 and X2 is the same. And so, since X1 is a sum of m out of the m plus n, it certainly is extremely natural to say that X1 explains a fraction m out of m plus n. And now I can give a few more axioms that drive you to that a little bit more, but it doesn't seem very objectionable to me. Okay. Now, I can now say I've started with a symmetric m plus n variable problem, and I've gone to an unsymmetric 2-variable problem. But I can now calculate the variances and covariances of the 2 variables, and if I'm going to have a sensible general answer to this problem, it should be one that agrees with this. That is, that when I have 2 variables with the kind of variance and covariances that I get out of this, that it will assign a fraction m over m plus n to x1 and the rest to x2. Now, so it's a straightforward calculation what the variances and covariances are, and I don't know that I need to repeat it, but nor do I know whether this is legible in the back. But in any case, I have here the variance of x1 is easily calculated in terms of the m and the n and the r and the sigma squared, and the variance of the x2 and the correlation. And so now I say that, well, let me go one more step. Suppose I let z1 be 1 over beta 1 x1, and similarly for z2. Then, I started with variables that had equal variances. These variables don't. I might want to start with, say, a standardized problem. So if if I start with a standardized problem in which z1 and z2 each have variance 1, then I can relate that to this problem. That is, here, x1 had variance beta 1 squared, so I can rewrite it if I take z1 to be x1 over beta 1. That's the standardized variable. I can rewrite it in terms of the standardized variables. So now I claim that if I have any problem, any two-variable problem, and I rewrite it in terms of standardized variables, I now have a way to partition the variance explained between the two, which is presumably forced by the equivalence to a problem of symmetry. Now, the question would be, what problems are equivalent? Or what would be even more embarrassing would be if two different problems could be equivalent and give different answers. But that embarrassment doesn't occur, and in fact, you can always take a two-variable problem and re-express it in a form that could have arisen in this way from a symmetric problem with one condition to be mentioned. When you solve, now going from the, if you had started with this problem and said what problem of this symmetric type could have given rise to it, and you solve back, you find that you can get a solution, and that the ratio m to n is the ratio of, is the same as the ratio beta 1 times beta 1 plus rho beta 2 for the first variable over the same thing for the second variable. So as long as those two, as long as the numerator is positive and the denominator is positive, then I can get this problem from a symmetric problem. So I am requiring that the numerator and denominator be positive. Now, to interpret those, I might point out that beta 1, well, it has several interpretations. One is that it's the regression coefficient of a standardized variable. Another would be that if you think of what is the variance of this term, so this might have been b1 x1 if x1 wasn't standardized. Well, the variance of that term is the same as the coefficient of the standardized variable, or the square of that coefficient. So you can think of it in that form as well, or as a standard deviation of the direct effect term. And what is beta 1 plus rho beta 2? Well, if I were to regress on z1 alone in this situation, when z1 and z2 have correlation rho, then the coefficient of z1 alone would be beta 1 plus rho beta 2. So it is just the standardized coefficient of, I don't know whether you'd call it the marginal regression, but in any case, the regression on that variable alone, it's the coefficient when that variable is standardized. So it would be correlation coefficient if y were also standardized. I could have standardized y throughout, though any formula like this ratio won't depend on whether the y is standardized. Okay, so the main, or one of the main steps, I guess I would say the main step in my argument is that if you want a general procedure for partitioning variance explained between the explanatory variables, then this consideration takes you from symmetry to this particular partitioning where you multiply, you assign an importance to each variable that's proportional to the product of the coefficient of the direct effect and the total effect in standardized units, that is, standard deviation standardized units of that variable. Okay. Now, let me discuss briefly. So I think I get this. Let's just do it. Let me remark before I get into however much of that I get into, that to go from more than two variables to two variables does require some additional step. One thing, but the main thing that's involved is to say, well, the variance explained by one subset of variables wouldn't be changed. The importance of one subset of the variables wouldn't be changed by a non-singular linear transformation of the other variables. And that kind of enables you to reduce any subset of the variables to the terms in the full regression that belong to that set of variables as one variable, and then essentially noise variables besides. And if you argue that noise variables have no relative importance, then you can argue, reduce the general case to the two variable case. And this quantity, which is in effect the coefficient of that variable by itself plus the marginal coefficient in the marginal regression, that obviously extends to any number of variables. And that extension, as I say, I won't discuss in detail, but it certainly is very natural. Okay, so this rule is an old familiar rule, and one way to look at it is to say that if you partition the whole of maybe I'd better put that up where you can see more. If you take the whole of the variance explained, so the sum of bi xi or beta I zi, not being careful about the notation, but you can guess. If you write that variance as a sum of all the covariance terms, counting the I and j and I separately, or in this form, the variance and twice the covariance terms, then for each variable, you are taking its variance term and one of the two covariance terms and attaching it to that variable, and the other of the two covariance terms you give to the other variable. And that comes to the same formula. Or if you like, the part of the variance explained by zi is the covariance of the direct term with the total. This sum of beta j, zj is in fact the regression on all variables. So there are various different ways that you can think of what this formula is doing. It's a well-known formula that if you sum the coefficient of a variable times its, say, correlation with y, that you get essentially the total variance explained. But that seems that rule of assigning that quantity as the importance of that variable seems not to have been held in high regard, according to what I've been reading. And I get it as really the only thing, if there is a solution to this problem, and that you might argue that there really isn't one, if there is a solution to this problem, that has got to be what the solution is. Now let me mention one other type of interpretation of this measure. Suppose, and this is, Kruskal is interested in the idea of averaging something over all of the orderings, and my colleague Robert Schlafer is interested in the idea that the only kind of a problem that would make any sense here is to say how much would the variance of y be reduced if I were in a position to fix one of the x's, or some subset of the x's. Now, for that to make any sense, the x's have to be factors that are under your control, but you haven't been controlling. They've been occurring randomly in the past, and you say if you went about controlling one of the x's and fixing it, what would happen to the variance? Okay. Now, if I combine those two approaches, I come back to this same measure, and let me just show you the way that goes. If I were to fix the variables x1 up through xi minus 1, so that means those terms in the regression no longer vary. And the remaining terms, the bj, xj, for j greater than or equal to, I guess I said I was fixing these, greater than or equal to I, those terms still vary. So the variance of y would now be, if none of the conditional distributions are changed when you fix something, the variance of y would be now this quantity plus the residual variance. If I say, okay, I'm now going to fix xi as well, the variance of y will become this quantity plus the residual variance. So the gain, the reduction in variance of y due to fixing xi after fixing x1 through xi minus 1 is this difference. Now that is the variance of the direct effect term plus twice the covariances with all the later x's, the ones that are not fixed. Okay? And that too is indeed there. But now if I say to myself, well, I could fix all of them and I could fix in any order, and maybe I should give xi credit for what it would do if I took the variables in random order and saw how much the variance was reduced when I got to xi, then you can see that in a random order, there's a 50% chance that any given other variable will precede xi and a 50% chance that it will follow. So that 50% times that 2 becomes a 1, and the average over all the orderings is this same term that I got before. So this is another interpretation of this same measure, that it's a kind of an average over all possible orders in which you might bring in the variables of how much the variance of y would be reduced when you bring in xi. Now, this, in fact, can perfectly well be negative. And indeed, that's one of the things that has bothered people about this measure. In fact, it may be, this would be my psychiatric conjecture, the reason that people have thought so little of this measure, if they have thought so little of it, is because they could see it could be negative, and how can a fraction of variance explained be negative? Well, I would say that, well, first of all, in this interpretation, it perfectly well can be negative. It can be that on average the variance goes up when you fix one of the variables because of some negative correlation of that variable with others. It can, but another reason that I would say that negative fractions of variance explained are perhaps not such a bad thing is that it's obviously an oversimplification to be trying to describe the variance explained or attribute variance explained in a sort of one-dimensional way to the variables. And if the possibility of a negative sign is just a reflection of that oversimplification, and if a negative term did occur, that would be perhaps a signal that you were in difficulty with your one-dimensional view of a multidimensional problem. But of course, you could be in difficulty. It's not a necessary and sufficient signal, if you like. In fact, in an example that when I ran the Yule data, I found in most cases, I think, one of the terms in a three-variable problem, one of the terms comes out to be close to zero but negative. Well, that's not so bad because that variable, you would say, was pretty unimportant anyway, perhaps. But and you certainly could also have situations in which they happen to have the same sign, but there was a lot of cancellation involved in these terms, and therefore, presumably, a lot of misrepresentation, or at least a lot of oversimplification in representing all of this by a single term. So the last idea I'd like to leave you with is that perhaps the next step in this kind of an analysis would be to find some good measure of, some natural measure of the oversimplification that's involved when you try to attribute importance to the various variables. Just as I would say, in a sense, if you think of a mean as representing a population, the standard deviation is telling you how much of an oversimplification it is. It's one measure of how much of an oversimplification it is to represent that whole population just by its mean. Thank you.